Okay, so to pick up part 2 of homework 1-3, we'll pick up here with questions 8, 9, and 10. So this one is a good example for illustrating exactly how we can find our c, right, when we have to do integration. So they give us the acceleration function, where t is in seconds. They tell us the object is at rest, so we know its velocity is 0 at a time of 0. And then they ask us what is the velocity of the object at time 6 seconds. So again, the important concept here is I'm going to start with my acceleration function. In order to find the velocity at 6 seconds, to find the instantaneous velocity at 6 seconds, I need to find my velocity function. So if a of t equals, and I'm going to go ahead and drop the units just to get it a little bit simpler. So 3.00 t, right? In order to go from the acceleration to the velocity function, I need to integrate this with respect to t. So I'm going to integrate this with respect to t. So in doing so, I find my velocity as a function of t. Integrating, right, that's where we increase the power and then divide by that new power. So this would be 3 divided by 2, t squared, but then I do have that plus c hanging around. And the plus c is very important because we cannot just assume that it's going to be 0 or 1 or 6 or whatever it may be, right? We have to be able to definitively show what c is. And that's where this information comes into play. We know that at a time of 0 seconds, the velocity should be 0 because the object was at rest. So I know that when I plug in 0 seconds, I should also get 0 on the left-hand side of the equation because the whole velocity was 0. So 0 equals 3/2 instead of t, I'm plugging in 0. And then again, this definitively shows me that, obviously everything cancels out here, so this shows me that c is in fact 0. But if I didn't know that information, I wouldn't be able to find the exact velocity at 6 seconds. So this tells me that c is 0. So my actual velocity function then is v of t equals 3/2 t squared plus 0, or you can obviously just drop the 0 since it's just plus 0. So in any case, I've got v of t equals 3/2 t squared. They asked me to find the velocity of the object at 6 seconds. So v of 6, I'm finding my velocity at 6 seconds, equals 3/2 6 squared. Obviously 6 squared is just 36. Half of that is 18, and then times 3 is 54. Okay, so my velocity of 6 seconds is 54 meters per second. Okay, so hopefully not too bad, right? Hopefully not too bad. The very key element though, don't overgeneralize this too much. You do have to be able to specifically find c. So there's question 8. I meant to do this on question 9 and I forgot to, but the correct answer on question 9 here, and question 8 is what I meant. Correct answer on question 9 should have been positive 4.15 meters per second, or 4.15 meters per second, the original direction. So if you got that answer and again are confident with it, feel free to skip this example. If you did not get that answer or just want to review it, I will continue to work it. So it tells us the ball rolls across the floor here with an acceleration of 0.100 meters per second squared in the direction opposite to the velocity. So the ball has a velocity of 4.00 meters per second, rolling a distance of 6 meters across the floor. What was the initial speed of the ball? The fact that this is opposite, right, the key that tells me is the acceleration is not just 0.100, but it's negative 0.100, at least as long as I'm defining this velocity as positive. So they're giving me here the final velocity. So the final velocity is 4.00 meters per second. And then they told me the displacement, right? That was after 6 meters that it had rolled across the floor. So at this point, this is truly a pretty easy kinematics equation. You have 3 of your pieces of information, so you could go back through and find either the initial velocity or the time if need be. In this case, they want us to find the initial velocity. So relating these 3 to the initial velocity, the easiest equation to do that is my final velocity squared equals my initial velocity squared plus 2a delta x, right, my change in displacement. My final velocity I know is 4, so I'm squaring that. My initial velocity is what I'm looking for. 2, it is once again very important here that I include the negative with the acceleration and then my displacement of 6. So at this point, I trust that you guys can calculate, right? Just solve this out, calculate this out. When we solve for it, we get v sub 0 squared equals 17.2. So then when we square root both sides, that's where I get 4.15 meters per second. And the fact that this ends up being a positive quantity tells me again it was moving in the same direction as this final velocity was moving here. Okay, so hopefully this one wasn't too bad and a good chance to review what we'd seen last year. Similarly, 10 is another question that should have been reviewed for most of us. Okay, so the soccer balls are released from rest at top. I'll go ahead and again give the answers. So part A, the acceleration should be 2.35 meters per second squared. If you are confident with that answer, good. Part B, the correct answer should have been about 108.3 meters, or obviously depending on where you rounded that, maybe just 108 meters. Okay, so for the total length of the incline. So if you need to see either of those two parts, stay tuned. Otherwise, congratulations, you are done with this video. So working through part A, they give me after 8.6 seconds. So for part A here, they told me the first period of time is 8.6 seconds. We know that it started at rest, so the initial velocity is 0. They tell me that it travels a displacement of 87 meters down the ramp. And then after 1 seconds later, that's when they get to the rest of it. And so to find the magnitude of the acceleration, again, I have 1, 2, 3 pieces of information. So if I want to find the acceleration, I just use any of my kinematics equations that can help me out. So in this case, if I use the delta x equation, delta x equals v sub 0t plus 1/2 at squared. The initial velocity is 0, so that cancels out. My displacement was 87 meters. I'm looking for my acceleration, but I know that time was 8.6 squared. So once again, it's just the algebra, right? It's 8.6 squared, half of that, and then 87 divided by that quantity. So that's where I got my 2.35 meters per second squared for the acceleration. So then for part B, there are a couple different ways you could do this. One way would be you could find just that last 1 second. So if you were doing it that way, you could find the initial velocity for that final second. You could use the same acceleration, use the second, and then figure out the distance. The easiest way though would be, let's just reset this all the way from the beginning. If I go all the way back to the beginning, I'm looking for how long the total ramp was, right? But I know that the total time that it takes to reach the bottom is, or the hill I should say, but the total time that it takes to reach the bottom would be my 8.6 plus the additional 1 second, so in other words, 9.6. I now know my constant acceleration, right? They told us it was a constant acceleration. I just found that to be 2.35 meters per second squared. And once again, if I go all the way back to the original context, I know the initial velocity is 0. So this time I'm just going to reset. I'm going to do the exact same equation, but since I now know the acceleration, I'm going to use my new total time to find the total distance. So delta x equals, again, v sub 0t, which would once again cancel out, plus 1/2 at squared. So plugging in our measurements, delta x equals 1/2 the acceleration that we found of 2.35 times the total time of 9.6 squared, and that's where I got my measurement of 108.3 meters. Okay, so again, this is not by any means the only method you could use to find that final distance there, but this is perhaps the easiest way to find the total distance of the incline. So hopefully questions 9 and 10 were just a good chance to review what we saw last year. If you do have any questions over any of this material, obviously come find me. Keep in mind that I do have a meeting tomorrow morning. Obviously this is for the 2015-2016 school year, but I do have a meeting tomorrow morning.